integral between T1 and TVL dt will be negative because VL remains negative throughout this interval. So that area, let me mark it as A minus. So A plus plus A minus should be equal to 0. Hello, welcome to Understanding Power Electronics. In this video, we will see a neat little idea called Voltsecond balance. Consider an inductor. Inductors are often used in power electronics. Usually in power electronics, air-core inductors are not used. So there will be a core, ferrite or some such suitable material. So this is a core and turns a winding. The terminal voltage is VL and the winding resistance RW has been shown separately here. Of course, it's a distributed resistance which is distributed throughout the winding, but for modeling purposes, we show the winding resistance separately. This is the inductance symbol, as we all know, and L is the inductance. The unit of inductance is Henry, voltage VL, and the current through the inductor. Now, because of the voltage VL, there will be a current that is drawn by the inductor. It is IL, let's mark it here, and this IL will cause a flux to occur in the core. Flux is measured in Weber, W-E-B-E-R. Now if the voltage is changing, that is VL is changing, then IL will change with time, and the changing IL will produce a changing flux. And according to Faraday's law, time varying flux will cause an induced voltage. We are assuming that the whole of the flux is coupling with every turn in the coil. So according to Faraday's law, induced voltage EL, that is EL here, will be N d phi by dt. So this is true whether the core is linear or not. Even taking into account the nonlinearities in the core hysteresis, core saturation, still this Faraday's law, EL is equal to N d phi by dt, that will be valid. Suppose the core is linear, what does that mean? That means B is proportional to H, where B is the flux density, flux phi divided by the cross-sectional area A. H is the magnetic field intensity. So H is proportional to the current IL. B proportional to H means the same as phi proportional to IL. So d phi by dt is proportional to dIL by dt. So EL will be proportional to dIL by dt. So you know that form of EL already. EL is L dIL by dt. The proportionality constant is L, the inductance of this coil. Here the inductance is a constant value because we have assumed linearity of the core. So we will see the Voltsecond balance both from flux point of view and from IL point of view. Flux point of view, the core can be nonlinear. From IL point of view also, the core can be nonlinear, but we will see it when the core is linear because it is easier to see and understand. That's all. We have assumed that the winding has a resistance RW and we have shown it separately. So because of that, the induced voltage and the terminal voltage are different. But usually the winding resistance will be pretty small. So let's neglect the winding resistance. Once we neglect the winding resistance, the induced voltage and the terminal voltage are the same. So then VL will be equal to EL, and these equations can be expressed in terms of VL. VL is N d phi by dt equal to L d IL by dt. Next, let's consider an inductor in a circuit in steady state. That means all the DC voltages and currents are constant. AC values have reached steady state. This implies that the AC ripple introduced by the power electronic switching is in steady state. So let us plot the flux waveform and the voltage waveform. So the flux waveform has a DC component and a AC ripple component as shown. It is assumed to have that. The unit of flux is of course Weber. I have not shown the values of flux here. The arguments are valid irrespective of the actual values. Given the flux waveform, we can find the voltage waveform as being equal to n d phi by dt. Now let's get an idea of how the voltage waveform is going to look like. We are starting at a flux of phi naught. The flux waveform is at a minimum here. The slope of the flux d phi by dt is 0 here, and because it is 0, the voltage will be 0 at t equal to 0. The flux increases and it reaches a peak value of phi p at time t1. Between 0 and t1, the flux is continuously increasing. d phi by dt is always positive. Between 0 and t1, VL will remain positive. Somewhere here, the slope is maximum. So at that point, we can expect the peak voltage to occur. The voltage will start from 0 here, reach a peak somewhere here, and return to 0 here, because the slope is once more 0 here. Between T1 and capital T, the slope is always negative, so the voltage VL will be negative. In addition, there is a small wiggle here, so that will introduce a wiggle in the voltage. The voltage will be 0 here. Once again, the voltage will be 0 here because the slope d phi by dt is again 0 here. And between T1 and T, the voltage VL will stay negative and the voltage will have a small wiggle because of the wiggle in the flux. The flux at T is phi T, and of course phi T is equal to phi naught. Let's see how we have done in anticipating the voltage waveform. The voltage waveform is as we expect, starts from 0, reaches a peak, comes back to 0 here, and then stays negative till time equals capital T, and there is a small wiggle in the voltage. Now let's recast this equation in differential form. So 1 over n VL dt equals d phi. This is the same equation as this in differential form. Once I have this, I can integrate both sides between time equal to 0 and time equal to capital T, that is over one period. Here the variable is t, so I can integrate between 0 and capital T. Here the variable is phi, so I have to choose the corresponding values of phi. So at time equal to 0, phi will be phi naught. When time equal to capital T, phi will be equal to phi t. So doing that, 1 over n integral 0 to t VL dt will be integral phi 0 to phi t d phi. Integral of d phi is of course phi, and when I apply the limits, this will become phi t minus phi naught, and we know that we are in cyclic steady state, so phi t will be equal to phi naught, so this will go to 0. So that means integral 0 to t VL dt is 0. So the integral of the voltage waveform of any inductor, and we will see for a transformer also, the integral of the voltage waveform over a cycle under steady state will be 0. This is Voltsecond balance. A very logical and simple idea but useful. The reason why it is called as Voltsecond balance, the use of the word balance, we will see shortly. Now we will understand a bit more about this Voltsecond balance. First is core resetting. Core resetting is a phrase which you might hear sometimes in power electronics. What do we mean by that? Notice that the flux at the end of the cycle is the same as the flux at the start. That is core resetting. Let's say the core flux does not come back. Phi t is a little bit more than phi naught. So at the next cycle it will be even more. At the next cycle it will be even more until the core goes into saturation. This phenomenon is called flux crawling because the flux simply crawls all the way to saturation. This is to be avoided, and in power electronics sometimes we need to take special measures, particularly in transformers, to make sure that the flux crawling does not occur and that the core is reset in every cycle. Sometimes the flux does not voluntarily return in power electronics, so you need to do something to make it return. That is core resetting. Next we will see a little bit more about this integral and what it means. So this is Voltsecond balance. Integral 0 to t VL dt is equal to 0. Now I can take this integral. The integral is between 0 and time equal to capital T. I can divide it into two intervals, 0 and t1 and t1 and t, and write the integral accordingly. 0 and t1 VL dt plus t1 to t VL dt equals 0. Integral between 0 and t1 VL dt, this integral is going to be a positive value because VL remains positive throughout this interval. Let me mark it as a plus here. Integral between t1 and t VL dt will be negative because VL remains negative throughout this interval. So that area, let me mark it as a minus. So a plus plus a minus should be equal to 0. So the positive area and the negative area should add up to 0. So the positive area magnitude and the negative area magnitude should balance out. That's why the word balance is used here. The positive area magnitude should be equal to the negative area magnitude. Because this is so, this idea is also known as equal area criterion. Next we will see the same Voltseconds criterion from current point of view. In this case we will simplify as we talked earlier. We will assume that the core is linear. It is only for understanding purposes we are making this assumption. Phi is proportional to IL as we saw before. So let's plot the current waveform. It's going to have the same shape as the flux waveform. It will start from a minimum I0, reach a peak of IP and return to a value IT, which should be the same as I0. And Faraday's law can be written as VL equal to L dIL by dt, where L is a constant inductance because we have assumed linear core. Now we can describe how we get the voltage waveform using the current waveform the same way as we did with the flux waveform. Between 0 and T1, the current slope is always positive, the voltage remains positive, and so on. Now we can also express this equation in differential form. 1 over L VL dt equals dIL, and then I can integrate between 0 and t. 1 over L integral 0 to t VL dt is integral I0 to IT dIL. That will be IT minus I0. That will be 0. We just follow the same steps as we did with the flux case here also. That shows that integral 0 to t VL dt is 0. So we get Voltsecond balance using this equation also. So with this approach also, we can show that the magnitude of the positive area will be equal to the magnitude of the negative area. You might know that you cannot apply DC voltage to an inductor. So how is that idea related to this Voltsecond balance? So we are showing the inductor again here, and we are showing all the plots here, the flux plot, the voltage plot, and the current plot. So what is the average inductor voltage? Average voltage under steady state and the DC voltage are the same. The average voltage equals 1 over T integral 0 to T VL dt, and we know that this integral is 0, Voltsecond is 0. So average voltage will be 0. There cannot be DC voltage across an inductor under steady state because Voltseconds is 0. So the idea of Voltsecond balance and the idea of there cannot be a DC voltage, both are identical ideas. We are talking about the same thing in slightly different ways. Now what if there is a DC voltage? Okay, then since VL equals L dIL by dt, we can expect VL average will be L dIL average by dt. I am applying some kind of superposition there. So VL average is L dIL average by dt, and we are assuming that this VL average is non-zero, let's say some constant value. You can find out IL average by knowing the VL average and integrating it. So IL average equals, I am bringing the L over to this side, 1 over L, integral 0 to T VL average dt plus C, that is the initial value of the IL average at T equal to 0. That's not important, we need not worry about it. VL average is a constant value, so this will be VL average by L times T plus C. So as T progresses, average current will keep on increasing. So your source will fail, components will fail. Likewise, the flux is going to increase and the core will be driven to saturation. So this is not acceptable. So independent of our previous discussion, the average voltage across the inductor cannot be non-zero. So that means VL average has to be 0. That means the Voltseconds balance has to be maintained. So you can approach the Voltsecond balance straight away from the idea that you cannot have a DC voltage. So it's a chicken and egg thing. Do you assume that the waveforms are repeated under steady state? From there you obtain Voltsecond balance, and from there you come to the DC average voltage being equal to 0? Or do you go the other way, start straight away with the problem of having DC average voltage non-zero, thereby show that DC average voltage has to be 0, and thereby Voltsecond balance has to be there? Either way is fine. Next we will see how this Voltseconds balance idea applies to a transformer. This is a core with 2 windings, so it's a 2-winding transformer. This is the primary winding, this is the secondary winding we can take, and N1 and N2 are the turns. Now V1 is the primary voltage, V2 is the secondary voltage, I1 is the primary current, I2 is the secondary current, N1 I1 is the primary magnetomotive force or MMF, N2 I2 is the secondary MMF or magnetomotive force. These two will cancel out almost totally, but there will be a small difference. That difference drives the flux in the core. So the flux is phi. We will make some simplifying assumptions so as to easily understand what is going on. One assumption we will make is that there is no leakage flux. Because of this, in the equivalent circuit, you will find that the leakage inductances will be absent. The second assumption that we will make is that the core is linear. There is no hysteresis, there is no magnetic saturation. The flux is proportional to the magnetizing MMF, the flux is proportional to the magnetizing current. The third assumption that we will make is that the resistance of the winding is negligible, so we will neglect it. So these are the three assumptions we will make, and we will draw a simplified equivalent circuit, and we will understand the Voltsecond balance in a transformer from the equivalent circuit perspective. So this is the simplified equivalent circuit. There is no leakage inductances, there is no winding resistances, and any resistance to depict the core loss will be missing from this equivalent circuit. So the equivalent circuit is very simple. An ideal transformer and a magnetizing inductance. This is the equivalent circuit. This is a model. There is no separate magnetizing inductance in the transformer. Now this ideal transformer with N1 N2 ratio, output voltage V2, output current I2, I2 prime or I2 dash, that is the reflected secondary current on the primary. That is I2 times N2 by N1 will be I2 dash. That comes from MMF balance, because this is an ideal transformer. N2 I2 equals N1 I2 dash at every instant. The primary also takes an additional current in order to magnetize the core. That represents the additional MMF that drives the flux. The whole transformer is represented now by a parallel circuit. A magnetizing inductance in parallel with an ideal transformer. So the ideal transformer and its load is one element of the parallel circuit. The other element is the inductor. So you have a situation where you are applying a voltage to the inductor. So whatever we learned from Voltsecond balance in an inductor is applicable now to this magnetizing inductance in this equivalent circuit. So I can write the Faraday's law. V1, which is the applied voltage, is N1 d phi by dt. N1 is the number of turns, phi is the flux in the core. That is be equal to Lm, the magnetizing inductance, dim, the magnetizing current, not the whole current, but the magnetizing current by dt. Voltsecond balance will follow. The integral V1 dt between 0 and t will be 0. So for an arbitrary phi waveform, we can draw the phi waveform, Im waveform, and the V1 waveform. So that is shown here. This is the flux. I have taken the flux waveform arbitrarily. At phi naught, the voltage will be 0 because d phi by dt will be 0. At t1, voltage will be 0 again because the d phi by dt is 0. So the voltage waveform goes through a peak and comes back to 0. And between t1 and t, the flux is going down, so the voltage will be negative, and so on. So you can explain the voltage waveform either with the phi waveform, flux waveform, or using the current waveform. So from this, following the same method that we did earlier, we can get integral 0 to capital T V1 dt equals to 0. In this case, because V1 and V2 follow each other, integral V2 dt is also 0. So if you have any number of windings in a transformer, at every winding, the Voltsecond balance has to be maintained. And likewise, this area plus this area has to be 0. So A plus plus A minus has to be 0 in a transformer also. Lastly, there cannot be a DC voltage across any of the windings of the transformer. If there is, the average current will keep building up and the core flux will keep building up until it goes to saturation. So what is the use of this idea of Voltsecond balance and Voltsecond in general? Now we will see a few examples of places where Voltsecond balance and Voltsecond are used in power electronics. One of them is in determining voltage ratio in power converters, particularly DC to DC power converters, voltage ratio between output DC voltage and input DC voltage, and also capacitor DC voltage and input DC voltage, for example. Let's take a DC to DC buck converter. The input voltage is Vin, the output voltage is V0. We are assuming that the capacitor value is large enough that the voltage V0 is fairly constant, is DC, with a very slight ripple which we neglect. That ripple occurs because of the switching. We do not know V0 and we wish to determine V0. We know that the switch is closed on and off at a duty cycle, let's say D. Let's say the switch is on, taking this as the common point. This side of the inductor is connected to Vin and this side of the inductor is connected to V0. So when the switch is on, the voltage across the inductor VL will be Vin minus V0. And when the switch is off, the inductor current freewheels through the diode, and if we neglect the diode voltage drop, then V0 will be applied to the inductor L in the reverse direction. That means inductor voltage VL will be minus V0. We are assuming continuous conduction mode of operation here. In case you haven't yet studied what continuous conduction mode is, don't worry about it. You can follow this discussion without knowing that. Now let me plot the VL waveform. VL waveform swings between Vin minus V0 and minus V0. This is the T on interval. This is the T off interval. And for T on interval, the voltage will be Vin minus V0. For T off interval, the voltage is minus V0. T on plus T off constitutes one period of switching, T, capital T. And T on by T is duty cycle. So T on is duty cycle times T. T off will be T minus T on or T minus dt. So T off will be 1 minus dt. Notice that it is relatively easy to come up with the inductor voltage waveform. The inductor is either connected to the source or to the load or both. So it's easy to plot the voltage waveform. By Voltseconds balance, we know that this area plus this area will be equal to 0, or A plus plus A minus will be equal to 0. A plus positive Voltseconds will be Vin minus V0 times T on. A minus, the negative Voltseconds area, will be minus V0 times T off. So I can write A plus plus A minus as Vin minus V0 times T on plus minus V0 times T off equal to 0. So T on is of course dt, T off is of course 1 minus dt. So I can rewrite this equation in this way. Now we can solve for V0 by Vn in this. V0 by Vn equal to D, which is known to many of us. As I said, it is relatively easy to determine the voltage waveform of the inductor. Then applying Voltsecond balance, we can determine the unknown DC voltage in the system. Another place where the idea of Voltsecond is often used is in determining current ripple in the inductor. This inductor is used in some power electronic circuit, and let's assume that the power converter is under steady state. And we know for the inductor VL is LdIL by dt. We are assuming that inductance value is constant. Then we can plot some voltage waveform and current waveform. The average inductor current is shown here, IL average. Now we would like to determine IP minus I naught. That is the delta IL, or the change in the inductor current. It's also called as the ripple current or peak to peak ripple current. Of course, it is the valley here, but please remember I naught value can be negative also. So in which case the ripple will be between negative peak to positive peak. So in general it is called as the peak to peak ripple current. This is an important parameter in the analysis and design of power converters. Since I want to determine the difference between IP and I naught, I need to integrate this between 0 and T1. First writing it in differential form, now integrating it 1 over L 0 to T1 VL dt, that will be integral DIL from I naught to IP. So this we know will be delta IL. This integral 0 to T1 VL dt we know is this positive area. So delta IL will be A plus by L, which is the same as A minus by L, the magnitude of that. Generally, as we pointed out, it is easier to plot the inductor voltage waveform, and from the inductor voltage waveform find the positive voltseconds or the negative voltseconds divided by the inductor value L, and we will get the peak to peak ripple current. This is an important parameter in the analysis and design of power converters. Delta IL tells us how effective the filtering by the inductor is. Also, if we know IL average and the delta IL together, we can find the peak current value, the maximum current value in the inductor, which is a useful parameter. Also remember, the same peak current will flow through switch or the diode. So the switch maximum current and the diode maximum current are also known. That helps us in the selection of the switch or the diode. The next example we will see is determination of the flux swing in transformer or an inductor. It shows the circuit symbol of a two-winding transformer, and by Faraday's law V1 is N1 d phi by dt. I can draw some waveforms for this transformer, the voltage waveform and the flux waveform. They are the same as what we used in our discussion of the transformer voltseconds earlier. We are assuming that the converter is operating under steady state. The flux swings from phi naught to phi p. Phi p occurs at time t equal to t1 and then comes down back again to phi t, and which is of course equal to phi naught. Now what we would like to find out is phi p minus phi naught. We have also assumed that the average value of the flux is non-zero. The average value of the flux can be non-zero. It is only that the average value of the voltage has to be zero. Now we would like to determine delta phi, the difference between phi p and phi naught. So for that I again write this in the differential form, 1 over n1 v1 dt equals d phi. I integrate both sides between 0 and t1. So when I do that, I get 1 over n1 0 to t1 v1 dt will be integral phi 0 to phi p d phi. This of course is going to be delta phi. This integral 0 to t1 v1 dt is the area A plus. So delta phi will be equal to A plus divided by n1 or A minus by n1, the magnitude of that. So it's very simple. Just draw the voltage waveform, which is relatively easy to find out. Draw the voltage waveform, find out the voltsecond area, positive or negative, and then divided by n1, you will get the flux swing. Divided by L, you will get the current swing. In the case of transformer, you will get the magnetizing current swing. Delta phi is a very useful parameter in the analysis and design of transformers. If I know the average flux, and then I know the delta phi, then I can find out maximum flux in the positive direction and maximum flux in the negative direction. If I divide that by the core cross-section area, I will find the maximum flux density. That is useful in determining how far away we are from core saturation. And also, delta phi together with the frequency of operation and the material characteristics determine the core power loss in the transformer. So delta phi is a useful parameter for designing transformers. As in this video, we have seen what Voltsecond balance is and how it is typically used in power electronics. If you find this video and the series of videos useful to you and interesting, please do consider subscribing to this channel and pressing the like button.